Okay, David.
Okay, welcome everybody to the new FPGA seminar season. So today we have Matthew Ann's work with Greg Stephan and Vaughn Betz on speeding up FPGA placement, parallel algorithms, and methods. Matthew.
Okay, thanks for the introduction. So as the title might suggest, the motivating question for this work is, why do we need parallel CAD for FPGAs? And one way to answer the question is to compare single-core CPU performance with FPGA size over the years. On this graph, the line shows the best integer spec benchmark score over the years, which is a reasonable indication of CPU performance. And the bars show the size of the largest FPGA commercially available. And we can see from this graph that CPU performance isn't keeping up with the growth in FPGA size. And the picture looks even worse when we consider interposer-based architectures, which build chips by stacking silicon dies on top of each other. And in this case, the takeaway is that FPGA CAD has to handle increasingly larger designs. And if we keep using the same algorithms for these designs, compile times will only get longer. The next question is to find out which step in the CAD flow is the most time-consuming. A design written in hardware description language has to go through synthesis, packing, placement, routing, various types of analyses before it becomes a bit stream that can be used to program a device. So recent results from the Titan benchmarks, which are among the largest circuits available for academic use, show us that placement on average is the most time-consuming step that Altera's Quartus 2 CAD flow takes. So placement is naturally a good choice for parallelism. The type of placement algorithm we'll be focusing on is based on simulated annealing. This is widely used, either for the entire placement engine, in the case of VPR and also Quartus 2, or for analytic placers. Simulated annealing is still used to fine-tune their results. The key computation in simulated annealing-based placement is the evaluation of a move. And a move is simply choosing a block from the circuit, moving it somewhere else on the circuit, and seeing how that affects the cost of the overall placement. If the move is accepted, the block stays in its new location. Otherwise, it goes back to where it was, and no change is made to the circuit. And a natural way to parallelize these moves is to have them evaluate in parallel on multiple threads. And in this example, moves 1 and 2, because they don't affect the same parts of the circuit, don't conflict. So they can safely evaluate in parallel. But in the example of moves 3 and 4, which try to move the same block to different locations, they have a conflict. And we can't accept results from conflicting moves, or we can end up with an illegal placement. So parallel placers have to deal with conflicts in some way. There has been plenty of previous work on dealing with conflicts in parallel placement. One of them is transactional VPR, or TVPR. And the interesting thing is it uses software transactional memory to speculatively evaluate moves in parallel. The nice thing about using software transactional memory is that it automatically handles any conflicts between moves. So from a programming perspective, it's easier than other techniques. In Quartus 2, the placer also speculatively evaluates moves in parallel, but the dependencies that can cause conflicts between these moves are tracked with manually written code. And it goes even further to try repairing any conflicts that occur to prevent wasted work. A slightly different approach, known as the half-box window technique by Goders et al., partitions the move space across threads and constrains each thread to only move blocks within its partition. And if it needs any data from outside its partition, it will use stale data so as to not cause a conflict. This is nice because the threads then can safely evaluate their own moves independently of each other. But the disadvantage is certain moves that may want to cross the entire chip will have a hard time doing so. Now, what's common about the prior work is that they either have limited speedup or they have significant quality loss. And most of them took a substantial amount of effort to code. So the question is, can we do better? What we want to do is find algorithms with better scaling and quality, and try to use transactional memory to simplify the coding effort. The first algorithm we have is very much like TVPR, and we call it move speculation, or move spec for short. And in this algorithm, we simply wrap an entire move in a transaction and use a transactional memory, or TM system, to monitor memory accesses made during each move. The system will detect conflicts automatically and also automatically roll back anything that conflicts. So the correctness of the resulting parallel placer is guaranteed. And from a programming perspective, it's very straightforward to apply a transaction to your code. So here's an example of how move speculation works. We start with threads 1 and 2. They each choose a block from the circuit and a destination to move the block to. And then they go ahead and move the block there without seeing any kind of conflict yet, because they haven't affected any other part of the circuit. But now we have a problem. Thread 1 moved block A and now wants to recompute the cost of connection AB, which is to say blocks A and B were originally connected. But at the same time, thread 2 moved block B elsewhere, and when thread 1 tries to read the location of block B, it finds that some other thread has changed it. And this, to the TM system, is a conflict. So what happens is either thread 1 has to roll back its transaction and restore block A, or thread 2 has to roll back and restore block B. Now here's another problem. If thread 2 retries the same move, it can cause thread 1 to roll back. And then thread 1, if it properly tries the same move as it tried earlier, can cause thread 2 to roll back. And we end up with an infinite loop, or in this case, a live lock. And to avoid that, what we do is, in this case, supposing that thread 2 had been rolled back, we get it to propose an entirely new move. This way, we won't end up with the same infinite loop that we would have gotten into earlier. Now, we implement move speculation using both software and hardware TM systems. The distinction between the two is in how they implement the conflict detection and resolution. In a software TM system, code within a transaction has to perform transactional reads and transactional writes, which are essentially library calls to the TM system for conflict detection. In a hardware TM system, conflicts are automatically monitored by the memory subsystem, and in the case of the platform we use, it's implemented in the cache. The advantage of a software TM system is that it's portable across various platforms, but the library calls add a certain amount of overhead, and that slows down execution. The advantage of a hardware TM system is it avoids the overhead, so it's fast, but it's not portable because it depends on specific hardware support. And since hardware has limited capacity, transactions can't use an unbounded amount of memory the way they can in software TM. A brief word about methodology. We test our parallel algorithms by parallelizing the BPR6 placer. We run experiments on an IBM BlueGene-Q compute node, which provides 64 hardware threads and support for hardware transactional memory. We average results over the 8 largest VTR benchmarks, the largest of which is just under 100,000 blocks. So to answer the question of how well this parallel algorithm does, we need to compare it to the performance of the sequential algorithm, which can make various trade-offs between execution time and quality. The black curve here shows what happens when we lower the effort, which is to say, have the placer run for less time, and the effect it would have on the quality of the overall placement. And we can see that with fewer moves, the placer takes less time, and the quality of the resulting placement gets worse. The dashed line shows what happens when we start off the annealing process with a low temperature, so that we avoid the usual hill climbing, and in cases of low effort, that can produce slightly better quality. So when we plot the performance of a different algorithm and compare it against the sequential one, if the curve lies above the black one, it's worse because its quality for the same amount of time is worse than the sequential one. And if it lies below the curve, it will be better than the sequential algorithm because its quality is better for the same amount of effort. So this is what happens when we run move speculation with software transactional memory. We see that it takes at least 8 threads to get any real speed up over the sequential algorithm. And even worse, beyond 8 threads, the quality degrades at a much faster rate than with the sequential algorithm. So this is not good news for the initial move spec algorithm.
Sorry.
Yes?
Catching these plots, the black thing you showed originally is the original uniprocessor algorithm.
That's correct.
And then the red one, you said something about speed up, but I'm confused where speed
Okay,
up is being
let's go
shown
back
here.
here. Yeah, so I'm referring to this point here. The data labels indicate the number of threads that we use to run the algorithm. And the data point being here means it takes less time, so on the horizontal axis, less time than the sequential algorithm with the default level of effort. So that's what I mean by getting speed up over the sequential algorithm.
So where is level of effort set? Oh, it's not being displayed.
That's not labeled.
So the actual execution time is on the x-axis, is that right?
Yes, the x-axis is the time. As you go to the left, naturally the level of effort decreases.
And
So in the parallel algorithm, you're not changing level of effort, you're changing number of threads.
That's correct.
In the sequential algorithm, you're changing level of effort. They both produce these trade-off curves, that's what you're saying.
Yes,
right?
that's the comparison being made here.
Does that make sense?
yeah, so the y-axis is wire length, right?
Normalized to the result you get from the sequential algorithm with its default level of effort.
Okay, so it's kind of looking worse than the normal algorithm.
It is, exactly.
But where's the time? I'm confused as that. I'm used to seeing time like that. The time
X-axis is runtime.
x-axis is runtime, so that point.
To the left means faster.
So it looks like the sequential algorithm is also faster.
You can make it as fast as you like.
So the black lines are changing interrupt on for the sequential algorithm.
Yeah, I was getting that.
And I think they
I should be
started,
able to understand.
they started an interrupt of 10 for the sequential algorithm, I think, right? Because that was the default in UBR6.
That used to be the case. I think for these experiments we adjusted it to 1.
Okay, so
That
it
was-
started at 1.
That
Okay.
became the default eventually.
Okay, I really am convinced that I need to understand. So can you point to the point, the rightmost point,
Okay.
the black point?
Yes.
on-
Yeah, so
and
this
tell me
here-
about that point.
This is the sequential algorithm with its inner num set to 1. So the quality you get is 1. That's our baseline.
And then so point at the 8 triangle.
Okay, the 8 is when we run a parallel algorithm with 8 threads here,
And what's inner num?
also 1.
Okay, so
We
the
don't
2 points
change.
I'm comparing are that triangle to that, like in my mind, I need to compare that 8 to that, 8 triangle to that square block. Is that
Yeah,
right?
that would be fair.
That's the thing that's, and because it's to the left, it's quicker.
It's a little quicker, yeah,
Oh, that's what I need.
but the quality is worse.
All these words, but it can happen quicker, okay.
Yep, so that's the idea here. That overall for this algorithm, we're not getting a better trade-off than the sequential algorithm is able to get us.
The points on the internum curve, are you, what do each of the points mean? Are you having some, like each of
As
those
you
black
go to
points
the left.
represents a different internum, so
That's correct.
what's the internum decreasing scheme that you're using?
In this case, it's just dividing by 2 for every point further to the left.
Okay.
So you roughly get even spacing between them on the horizontal axis.
Jonathan, I think some of your confusion may be an implicit assumption that this algorithm is gaining something. The answer
No,
is
I think I just realized it isn't.
worse in all conditions.
Yeah,
You
that
mentioned
that
the
goes
word
back
speed
to
up.
how we do the comparison from here, right?
You
Well-
did mention the word speed up, and that kind of threw me off.
It is faster before where's quality.
Yeah,
so.
then usually you don't claim
And you
success.
can get the same runtime by decreasing the number of moves on
Yeah.
a sequential algorithm.
Yeah, I'm starting to pick that up.
Okay. Well, if we're ready to move on, we can look at the other implementation of move speculation using hardware TM. And not surprisingly, it's much faster, further to the left, than the software TM implementation, but its quality is even worse. And we suspect that's because of the limited capacity, which is causing more transaction aborts than in the case of software TM. The conclusion we get is, from looking at both implementations of move speculation, taking this simple approach to parallelize placement with TM gives us good scaling, good speed up, I should say, but it loses too much quality, and it can't do better than the sequential algorithm with lower effort. And here's why we think the quality loss is so bad for this algorithm. Longer transactions to any transactional memory system are more likely to conflict with shorter ones. And what ends up happening in a parallel placer is the larger, more useful moves, which are in longer transactions, get abandoned more. And obviously that would result in a loss of quality because these more useful moves aren't getting evaluated properly. So one way to fix this may be to try making these transactions similar in duration so that they're all equally or more equally likely to conflict with each other. Yes?
How do you choose which thread to abandon? Because usually these are choices, right?
Yeah, and these are made non-deterministically, usually by the transactional memory system. So there's no deterministic, simple deterministic scheme you can make. You can specify to the system that the older one always wins, or the transaction that has done more work always wins. But overall, the effect the effect of selecting a policy here isn't going to matter to the overall quality. We're still getting this kind of favoritism toward shorter, simpler moves.
I hadn't thought of this before, but if you think of the bounding box update code, so what's monitoring wire length, the most CPU intensive case for that code, if it's a higher fan-out net, is when you actually reduce wire length, right? Based on the way the code is written, if wire length increases or does not change, it is able to essentially skip most of the computation.
Okay.
But the case where wire length might have decreased is actually the most expensive one. So that might actually link to this.
That makes sense. Yeah.
When you actually find something useful, it takes longer to prove it's useful.
And in doing so-
that happens only if it's a high fan-out net. For low fan-out nets, it's really not much different. But
Right.
so yeah, that is an unfortunate trait. When you find something good, it's more likely to be killed.
Apparently in this system. Yeah, as an aside, there is a quick fix to this problem by using hardware support. The BlueGene Q provides support for thread-level speculation, which behaves much like transactional memory, but it enforces the policy that on a conflict, the older transaction always wins. And furthermore, it makes the transactions commit in a fixed order, so that the execution is actually deterministic. In which case, the longer transactions, if they do conflict, will simply take longer to finish, but they still will, unlike what we have previously. And so the quality of placement is maintained using thread-level speculation. But unfortunately, the scaling with this technique is quite limited. The most we could get was a 2.2x speedup on 5 threads. So pursuing this further is not going to give us a highly scalable parallel placer. And we still have to go back to the idea of making transactions similar in duration to try addressing the quality issue. So that brings us to the second algorithm, proposal speculation, or PropSpec for short. And here the idea is to take the evaluation phase of the move computation out of the transaction by protecting it with tagged dependencies or a dependency check during the proposal phase. And when I say tagging a dependency, that works just like acquiring an exclusive lock on some part of the circuit. The difference is we don't let the thread stall if it fails to acquire the lock. Instead, if it fails to tag any dependency, we simply, just like before, let it abandon the move and try something different. The result is if a thread successfully tags all parts of the circuit that it might affect, it can safely evaluate its move without conflicts. So here again, the same example as before, but with a different algorithm. We start with threads 1 and 2, each choosing a block and proposing where to move them to. But instead of going ahead and moving the blocks, they first tag what they will affect. So in this case, it will be the block they're starting with and the location they want to go to. And because these blocks are connected to others via nets, the threads also have to tag those nets. And in this example, both of the threads will affect net AB, which is the connection between blocks A and B. And let's suppose thread 1 tags it first. Well, thread 2 would also want to tag it, but since thread 1 has grabbed it already, thread 2 has no choice but to abandon its move, untag its dependencies, and try something else. And in the meantime, thread 1, having tagged all of the block, the target location, and all of the nets that it will affect, can safely evaluate its move. And like before, when a thread encounters a conflict, it simply proposes a whole different move to avoid getting into live lock again. So we're going back to the same method of comparison. This time though, because the algorithm implements transactions that are similar in duration, we expect much better results for quality. And that is in fact what we get. Using the hardware transactional memory implementation and using up to 64 hardware threads, we get a 17x speedup with almost no loss in quality, which is encouraging. And what we can also do is get rid of the transaction entirely and replace all of the memory accesses with fine-grained locking operations, but we use lock-free techniques so that threads don't stall when they can't acquire a lock. And this turns out to perform even better than the hardware TM implementation, getting up to a 34x speedup.
I think,
Yes.
can you explain lock-free versus fine-grained locked? So, you give a
They
very brief
work in,
explanation.
yeah,
but-
okay. They work in essentially the same way. You still use some kind of data structure to represent a lock on some part of the circuit. But in the lock-free implementation, you don't use what you typically use, like a p-thread mutual exclusion lock, mutex, because that would stall if the lock is already taken by some other thread. In this case, you use an atomic operation that doesn't stall, and if it fails to get the lock, you simply move on and try something different. So that's the distinction. It takes a little more effort, not much more than fine-grained locking, to get a lock-free implementation working.
I thought that's what you described in your algorithm, that if you couldn't get the tag, you give up and change.
That's exactly it, yes.
So why didn't, when you said fine-grained lock, you said that meant you stalled on the lock?
Typically, a fine-grained locking algorithm would stall when, at some point, a thread tries to grab a lock that's already been taken by some other thread.
I see, but that's not what you described
That's
in
not
the
what
previous
we're doing
slide.
here.
That isn't what Matthew did. I was just getting the programming technique. He's comparing two programming techniques here. One is to use the hardware transactional memory, and one is to code using lock-free techniques to write more code to basically check the dependencies yourself.
Essentially, yes.
And they're saying that's similar to the difference of fine-grained locking. So it's not saying you did fine-grained locking.
Oh, okay.
So I was just asking to explain a little more what the distinction was.
No,
Okay, sounds good. So we conclude from looking at the implementations of this algorithm that the early dependency checking scheme we use is very effective. But the disadvantage of this algorithm is that it's completely non-deterministic. Proposals can conflict with each other at any time, and there's no guarantee which one succeeds and which one doesn't. So it would be nice if we can have a deterministic version of this. Which brings us to the last algorithm, serialized proposals, or serial prop for short. And the idea here is to get one thread, the master thread, to do all the proposals. That way, there's no possibility of having conflicts with another thread and introducing any non-determinism. And what we get all the other threads to do is only to evaluate the move that the master thread proposes. We use a fixed length task queue as essentially a reorder buffer to make sure that all the moves complete in a fixed order. And it's actually simpler than a reorder buffer because we keep it full at all times. We make sure there are always L moves in flight, where L is the length of this queue. Here's an example. We start with a queue of length 4, and there are 4 moves that have been already proposed and put in the queue. Their dependencies have all been tagged already. They don't conflict with each other, so any thread can take any of these moves to evaluate. And now the first move finishes evaluating, so it can move on to untagging its dependencies. And because there is space in the queue now, we can start proposing the next move, move 5. Suppose now that move 2 also finishes evaluating. We could also take it out of the queue immediately, but that means we don't maintain the guarantee of always having L moves in flight, and that would cause non-determinism again. So what we have to do is make sure that move 5 is completely proposed and put in the queue. And at this point, since the queue is full again, we can allow move 2 to leave and proceed to untagging. By guaranteeing that we have always L moves in flight, we see that the result of the placement only depends on the length of the queue and not the number of threads we use. And this length can actually be fine-tuned depending on the platform. So the result is not only deterministic, it's also, in this case, serially equivalent. And the speedup we get with serial prop is obviously less than with proposal speculation, because we're getting one thread to do only the proposals, and that becomes a bottleneck eventually. But the scaling we get is reasonable, nearly a 6x speedup on a total of 9 threads. So to sum up the original paper, we came up with 2 new parallel placement algorithms, one non-deterministic, proposal speculation, which achieves very good speedup, up to 34x, with a modest quality loss. We also have a deterministic version, serialized proposals, which gets reasonable scaling, up to a 5.9x speedup, with no quality loss on average. And unfortunately, our attempt to use a simple approach, the simple TM approach for move speculation, doesn't work out because it loses too much quality. But we're not stopping there. Before the paper was published, VPR7 was released, and so were the Titan benchmarks, which, as mentioned before, are some of the largest circuits available. So what we did from there led to new questions and new findings. So here again is our most scalable algorithm, proposal speculation, ported to VPR7 and run on the BlueGeneQ platform again. The curve looks similar. The quality loss is a little worse, but the self-relative speedup of 30x is still quite good. And just a note on interpreting this graph, which we did go through already, further down means a better quality of result, and further to the left means faster execution.
What are you normalizing to? Is that to internum 10 instead of internum 1?
That will come up, actually. That'll be in the next few slides. Okay, so we tried a different platform as well, the Intel Xeon Phi, which has even more cores than the BlueGeneQ. So it achieves an even more impressive 43x self-relative speedup. But it runs slower overall, so its absolute speedup still can't beat that of BlueGeneQ. And finally, we tried the algorithm on the Sandy Bridge platform, which has fewer, more powerful cores. But those run faster than the 2 near many-core architectures we looked at earlier. And what we get is that on Sandy Bridge, the results are the fastest of all. There's no way for the other architectures to beat them, no matter how many threads we use there. So to go back to the question of what the normalization factor is, the 1 here represents sequential execution on Sandy Bridge. So what we get is, the conclusion we get from this is that absolute performance is still best on the more commonly available platform with a few more powerful cores. And it seems to suggest that optimization efforts for parallel CAD should continue to target the commonly available platforms, not the many core ones that we tried earlier.
How many cores on the Sandy Bridge?
Just 16.
16,
Yeah.
so that's 6 out of 16.
Yes, so the scaling isn't as good because, for various reasons. One of them is that cross-chip communication, this is actually a two-socket system. The cross-chip communication latency is much worse than with the other platforms. So you don't get an impressive self-relative speedup, but the absolute speedup is still best.
So I don't know if you have graphs on this later, basically up to, you get 8 cores in one package, and your scaling's pretty good across that. But then
Yes.
going to the second package, the other 8 cores won't give nearly as much.
Yes, apparently. And even hyperthreading doesn't appear to help, unlike with the Blue Gene Q, where you actually want to use all the hardware threads. Switching gears a bit, there's an algorithmic optimization we incorporated since the beginning, and that was ignoring big nets. Big nets are typically associated with tall blocks in a heterogeneous architecture, and these are just high fan-out nets which are difficult to localize, and for a parallel placer they would cause the most conflicts. So the obvious thing to do is to ignore nets that are above a certain size, which means not tagging them during dependency checking and not computing their cost. So that naturally leads to fewer conflicts. But if we ignore too many of these nets, we'll lose too much quality. So setting the right threshold, the right size of net to ignore is important here.
I'm
Yes.
sorry, I don't quite understand the diagram. That looks more like you have a block of many nets as opposed to a block of a single high fan of net.
Oh, well, a net consists of a source block and its sink and its destinations. So in this case,
So the large blocks have multiple sources.
yeah, I guess you could put it that way.
So-
I meant to convey that it's just one source block to
Okay,
many
one source
destination
block.
blocks. Yeah,
One source pinned to many destinations.
yeah, that's actually how the net is supposed to work. It would look rather ugly drawn on here though. So my intention was to have one pin actually. Good point. So an alternative to this technique is to only ignore the bounding blocks, but not ignore any of the connections, because these connection conflicts are less common anyway. And even though this might take more work than ignoring the entire net, it might perform better in terms of quality. So here's our baseline. The net threshold we inherited from earlier work is that any net containing 10% or more of the blocks in the circuit gets ignored. Here is, as before, the 6x speedup on the Sandy Bridge platform. When we change the threshold to a fixed number, say 40 blocks or 20, we do lose a bit of quality, so the curve is slightly higher up on the graph, but the speedup does increase. So it looks like from this that a threshold different than 10% is probably more reasonable to use. And when we tried the alternative technique of only ignoring bounding boxes, again with thresholds 40 and 20, we see that the quality loss is surprisingly worse, especially for wire length. The picture isn't so clear for critical path delay, but that's a good sign that we're not losing too much quality in both of these metrics. A rather odd interaction is that, so going further to the left of the graph, we're using more cores, using more threads, and that seems to help with the loss in quality. That reduces the loss in quality from this ignoring bounding boxes technique. And it's not clear to us why this should be the case. Okay, another optimization technique we thought of was to divide the list of blocks used for choosing the starting block in a move. In VPR, there is a list that contains all the blocks in a circuit that can be moved, and the move generator, by default, just chooses a block at random from the entire list. But there is some locality between adjacent blocks in this list, and so blocks chosen that are chosen from close by are more likely to conflict. So what we can do is to divide up the list evenly among threads and constrain the move generator to use only the blocks from each of the partitions. That way we avoid choosing blocks that are next to each other too often. So when we do this, there is also an improvement to performance. The blue line here, labeled divide, is the technique I just described. And it actually performs better than other fancier ideas, such as partitioning the circuit using a graph partitioning tool, in this case H-metis, even applying weights to the graphic partitions. And both of those techniques don't do as well. In all cases, the quality isn't affected. So it seems like here that the simpler idea works better.
Sure, just to understand that distinction.
Okay.
Each medicine is dividing up the circuit in certain ways, and you only generate in the distinct areas. Is that the idea?
Yes.
And as opposed to just taking the ordered
The
list.
entire list.
And that order was created by
The packer.
the hacker.
Yeah.
But somehow it's ordered by how the person entered the code.
So it's the Packer net list, it's the order in which the Packer created the clusters.
Yeah, it's actually not the input to the packer, it's the output of the packer,
And
which
it
exhibits
orders
some locality.
it orders it by criticality, so Packer tries to pack the most critical things first.
Oh,
So
okay.
if you
Interesting.
divide it up and you have the most critical things, the Packer things early, and the less critical, timing critical things last.
Okay.
But locality is, somehow there's locality involved in that sequence.
Yeah.
That's why.
Yeah, somehow related logic tends to stay together in that list,
It's interesting. It's not always going to happen, but it happens.
which would completely ruin this technique if the packer decides to output things in a random order.
So maybe you should explain, I don't know if everyone understands like how the move generators changed to exploit this. Like you partitioned up the list of blocks,
Yeah,
and then if you have 4 threads, you have 4 partitions, and every thread chooses from a different partition,
that's right.
like all the time, so
That's
that
what
they,
this kind of diagram
that
shows.
there's less likelihood that you're starting
next to
from
each
the
other.
similar part of the circuit.
Yeah. It's a simple kind of constraint too. We're not saying that the entire move can only happen within this partition. It's only the starting block. So the destination can be another block elsewhere in the list in another partition. That doesn't concern us. The fact that doing this gives us quite a boost to speed up is rather surprising.
A question that sort of connects to that, if you could go back
Yeah,
and
here.
slide. Earlier on, when you said all the move generation was done by a single thread, that's still true, right? This is one thread that's proposing these things?
That depends on which algorithm you're talking about.
No.
So the comparisons here, we're focusing mostly on proposal speculation, where each thread does its own thing. So they have their own move generators. In this case, if you apply the default behavior, they're just all choosing uniformly from this entire list. So there's a good chance they'll collide or choose things that are very close to each other.
I thought you liked, oh no, that's right, the final algorithm you had in the previous section with the
The
single
single
thread
thread doing all
proposing
proposals, that's
had-
different.
Had less speed up, I guess, but
It
that's
has.
the determinism. But
Correct.
you're away from that now, now you're back to non-determinism?
Yes, just
Okay.
because it's the most scalable and want to see how we can do on the best platform we can get.
Okay.
So the final stop is seeing how the placer can scale to larger circuits. The largest VTR benchmark is just under 100,000 blocks, and the subset of the Titan benchmarks we were able to run range from somewhere around 90,000 to over 250,000 blocks, so quite a step higher in terms of size. And what we get running the 2 best algorithms we have is slightly better speed up on the Titan benchmarks. There's a rather marked gap here, actually, when you use more threads for the deterministic algorithm for the Titan benchmarks. So that's encouraging. So to wrap up the follow-up work, which is still ongoing, the first conclusion is that if absolute performance is the concern and you want the fastest possible parallel placement results, you should use a few powerful cores, not the many core platforms we've tried. And this is echoing results from earlier work that algorithm changes can improve performance mainly by reducing conflicts between moves, but it's important to find the right threshold to make a trade-off between quality and runtime. And from early results with the Titan benchmarks, we see that performance might actually improve with larger circuits. So that's encouraging for future work. And that concludes the seminar. Thank you very much.
Any questions?
Questions?
So in the serial prop, or I guess in general,
Oh,
what you're
okay.
saying is single thread performance is what's the limiting factor, right?
Yeah, that goes back quite a few
Single thread,
threads, quite a few slides.
a few more powerful cores. Just wondering if you know within a single thread, what's the limiting factor for that single thread?
For serial prop, it's the proposals. Doing
So what I mean, I'm wondering, like, is it memory bandwidth to the processor, or what is it stopping the thread to go faster?
Oh, that would take a lot more detailed analysis to find out. Chances are it's not just memory bandwidth. It could be a factor, but also that because we're making one thread do all the proposals, and there can be as many workers as we like, that one thread will eventually get too busy with just the proposals and not keep up with the other threads. So that's what we mean by proposals being a bottleneck. And that tends to be computationally intensive. Right?
So I'm just wondering, it's computationally rather
It
than
should
memory
be.
bandwidth.
Yeah, that's what we'd expect anyway.
My speculation would be it's memory latency there. The working set is fairly big and it is fairly random access.
So it's random access memory.
So I would expect it's more limited by memory latency
Mhm.
than computational or bandwidth.
A related question to that, I think, when you compare the best core that you're using to those many core things, the Blue Bean and
And
wherever
the
that call
Phi,
things.
yeah.
What's the ratio of their, those core performance, just rough?
I do have the frequencies plotted, but that's not the only indicator of their performance, of course.
What's
They're
the
single
first point on each curve? Is it 2 cores or 1 core? Or
On the far right, it's 2.
It's always at 2?
That's the minimum number you'd use for this algorithm.
So that gives you some rough, if you divide those two, does that tell you roughly,
It's an approximate number, yeah.
like a 12x or something?
Somewhat does, yeah. But it turns out when you run the original sequential placer on the Phi, it's something like a 43x slowdown compared to Sandy Bridge. So it's weird that with the parallel version, you immediately get some speed up on the Phi. Or rather, an advantage on the Phi over Sandy Bridge, if you can even look at it that way.
One place this kind of question leads is in the far future when you have, how many processors were in the Phi?
57.
57, so when you have 57 Sandy bridges, what's going to happen?
Then the problem will be interconnect latency. So there will be a lot of communication done, and if that's slow, you still won't get any kind of scaling. We're already seeing, so that if you look at this curve carefully, the spacing between the points is shrinking, even though we're doubling the number of cores with every point to the left.
Although, bad things happen, so that could be the case. But
Yeah.
the last point where things kind of compress on Sandy Bridge is where it's crossing between 2 chips.
Yes, of
So in
course.
the future, where you have, say, 64 Sandy Bridge cores on 1 chip, it's possible we get the optimistic result of, but until you get to you're
Which is
crossing the chip, you're actually getting pretty good scaling on Sandy Bridge. It's where you go to the other chip that you don't.
Apparently, yeah.
So
That's optimistic.
that's the optimistic,
It's
because I mean,
still
we're drawing straight lines from various points. But until you get to 8 cores, Sandy Bridge is scaling pretty well. And also, this result is before your final optimizations, I think.
It
right?
is,
So
that's right.
it's, the results are somewhat better already now. So,
Yeah, we can stretch things a little further to the left.
that said, obviously it gets harder and harder to maintain speedups as you put more cores on, so.
So I'm actually curious if you decide to do a more circuit by circuit breakdown ordered by heterogeneity. So I would expect that if a circuit had many big blocks that have many nets connected to it, then there's a higher chance of conflicts if you're moving those blocks. So circuits with lots of heterogeneity may behave very differently than circuits with, say, a lot more soft logic. So I was wondering if you've got a chance to do a breakdown of that.
That would be a good idea. This is all ongoing work after all, so I'll add that to the ideas to explore. Thanks for that. There's something I didn't plot in the Titan results, which is the quality difference. And for both of these algorithms, the average over the 10 benchmarks we could run is something like a 3 or 4% loss. And those come from mainly just 2 circuits, which suffer a 10% or more increase in critical path delay. So it does depend very much on the benchmark when you look at results.
Do you remember which circuits they were for VTR?
No, not VTR, for the Titan benchmarks. For VTR, there seem to be no outliers, though we can check again. For the Titan ones, the first is the Spark T1 core, which Just doesn't like any parallel algorithm. As soon as you use 2 or more threads, you immediately get a 10% loss in critical path.
RT1 is one with almost no heterogeneity, right? All soft logic.
That I don't know.
It's weird. I remember it had weird carry chain behavior and
Yeah.
weird memory behavior. So if you were to pick one outlier, you pick the right one. Because it's
Okay.
the easiest circuits to, I mean, it's a big Spark multiprocessor on an FPGA.
Oh.
That is an odd
Or is
thing
it
to
just the
do.
one core? There's a Spark T1 core and there's a Spark T1 chip, I believe.
Can't really know.
It's just the single core, I believe.
Yeah, it's just this, it should be anyway. It's low on the list of sizes.
But I would say it's still, you know, it is an odd benchmark. It behaves oddly. I know in the carry chain paper that Jason did, he excluded, well, we were checking Titan carry chain specific stats. Kevin got that for us and we excluded Spark as being weird. Like noted
Okay.
in a footnote of it's bizarre. So it's
Interesting.
an outlier in that case too.
Yeah, okay.
It does have a really long carry chain, so maybe that actually hurts you too. I mean, but it's odd in a few ways.
All right.
Anyway, so it's, yeah, if you're gonna, it's better to have no outliers, but if you're gonna have one, it's better to have one that's weird.
Yeah.
So.
But there's another, the other one is Dart, the network on chip, which also gets you something like the 10% loss in critical path as soon as you use more than one thread. Doesn't matter which algorithm. So there are definitely things going on in these benchmarks that the VTR ones have been represented.
Is that regardless of what you use as your fan-out threshold for ignoring nets?
I think so. And using 40 is being generous enough, so that didn't do the trick.
I've got a question about the third algorithm in the first chunk of things, when the single processor, single thread was proposing.
Okay.
The nets, did you say that it intentionally creates moves that don't conflict by construction?
It has to, obviously. If it,
So it tags things and reserves things, and the next one it selects, it avoids any kind of conflict, so it
that's
stops conflict from happening.
Exactly. It proactively does that, so the workers don't have to worry about conflict detection at all. It guarantees that everything it proposes can be passed off to workers which can safely evaluate in parallel.
So why does it need to tag anything, if that's true?
The tagging is to help it avoid the conflicts.
Oh, it's for its own processing?
Yes.
So
The workers don't
slaves
need to see the tags.
don't do that,
Correct.
But I don't know if that entirely answers what you're thinking. Like the algorithm does not intelligently figure out this would not conflict. It basically uses the tags to, it's doing its work, and then basically it sees, oh, this tag says this is not good, and it stops.
And it goes to another loop, I see.
Yeah,
Rather than
much-
proactively kind of working out in advance, if I do this, I guarantee no conflict.
Maybe some of the other stuff is heading towards when you're separate,
The partitioning ideas kind of get to that, yeah. Though we're not entirely going that direction. Okay, any more questions? Yep.
So if you're limited by, in the single-threaded performance, in that version of the master that's generating moves, have you pondered in any way to think about a smaller parallelization problem, parallelizing that problem on, say, 2 or 4 cores, in order to let you scale to 64, 128 cores or something?
Yeah, that's a good idea. Other people have already raised the point. And the simplest way, though not from a programming perspective, is to use thread-level speculation, which I've alluded to much earlier. You can get 2 masters proposing in parallel, and thread-level speculation will make sure conflicts get rolled back, and also that determinism is maintained. But to integrate that into the scheme we use for serialized proposals isn't all that easy. I guess a hybrid approach would be to make a software version, a software implementation of a very limited kind of TLS for this, just for this algorithm. So it can still do conflict detection, resolution, and then maintain determinism, but not be quite as powerful as a full thread-level speculation system.
It seems to me like if you can make those proposals faster than the workers are working, right? You just have a queue that, of jobs that the workers do. And just, so that the conflict resolution and that part, that can be done quicker than the average worker can consume jobs, and you can propose them fast enough.
Yeah, that would lead to better scalability, for sure.
It's comment.
Yeah.
It's very impressive,
Thank you.
Just a lot of different ideas and success. And I think it's neat that you kind of now understand, there's some drama to your 17 to 34, you went to, you had the 17.
Oh, from,
34.
yes, from
It's very nice.
that comparison, yeah.
That's maybe why you did that. But I think it's really impressive. I don't know if everyone knows that this won a best paper award at the conference I went to.
Okay, that's worth mentioning at the FCCM conference this year.
Yeah, I've never seen anyone present a graph before where they refused to explain the x-axis, but you did it and pulled it off.
No, he did not pull it up.
No, not the first one. I'm talking about like the normalized. What is that normalized to? I will get to that.
That was intentional.
It actually worked. No, I've never seen anyone do that before.
It's all relative. You're not supposed to worry about absolutes.
Okay,
All right,
great.
so-
So let's thank the booth.